Hello, welcome to this lecture on. This is the first lecture on viscous flow boundary. And in this lecture, I am discussing the boundary layer for an incompressible flow. Incompressible flow. And you know that when fluid flows over a solid surface, when fluid is flowing over a solid surface, consider a uniform flow. Consider a uniform flow approaching a solid body like this. Solid body like this. Of some free-stream velocity, some u infinity, and when you know that there could be a point called a stagnation point on the body surface, the fluid will be flowing like this. There is a potential flow like this, and the tangential velocity okay, tangential velocity corresponding to assuming that the flow has potential flow, let the potential of velocity is assumed as u. So that is a tangential velocity over the body surface, and that is a function of if you see the length along the body surface as x, and the u is a function of x. That is the potential of velocity is a function of x. Now, actually, it is not the potential flow we are considering. We are considering viscous flow. When we are considering viscous flow, the no slip condition is applicable. That means the fluid velocity becomes equal to zero on the solid wall. So let us consider the flow for the fluid velocity tangential in the direction of x, or a tangential direction to the body surface is denoted by u, denoted by small u, and the small u will be varying normal to the body surface. This is what I have marked is a direction normal to the body surface, that is denoted as y, and if that is denoted as y, the velocity would be varying like this, varying like this. So there will be a velocity variation normal to the body surface, and the velocity magnitudes u, that is the magnitude of velocity along the tangential, the component of velocity along the tangential direction to the body surface will be varying as a the function of y, that is distance normal to the solid wall, and it will reach at some y, it will reach the value uy reaches the value of a capital U. Capital U is called as the potential flow velocity at that particular x. So the fluid velocity will be attaining the potential flow velocity only at a certain distance normal to the solid surface. So within that layer, the velocity varies, and that layer is called boundary layer. Boundary layer. Boundary layer. And the first parameter related to the boundary layer is boundary layer thickness. Boundary layer thickness. Boundary layer thickness. It is denoted by delta, and the delta is the distance such that u at delta becomes equal to 99% of potential velocity. So the delta is the distance. Delta is the distance normal to the body surface where the fluid velocity u approaches 99% of capital U. That is considered as the boundary layer thickness delta. So that is how the boundary layer thickness is defined. Now let me draw this curved the distance along the curve x as a straight line distance, um, like this. To simplify the sketching of the boundary layer, let me draw it along this axis. So that is the developed distance. That is the curved distance is put along a straight line, and that is x. The normal direction can be marked as like this. normal direction, then we not, this is y direction, this is y direction, and let us assume that this is the forward stagnation point, that is this point, that is at x is equal to 0. This is at x is equal to 0, and we consider at some arbitrary x a lateral distance, and the velocity at x is equal to 0 would be the potential flow velocity is equal to the potential velocity u, and at certain x you will have the velocity at certain x you will have the velocity like this. So it will be like this, and this is the edge of the boundary layer. So within the boundary layer, the velocity varies as a function u of y. And let this point is denoted as A, B, A, C, C, this point is B, C, D. Let us draw a control volume also, like this. A, B, C, D is a control volume. Let's consider A, B, C, D as a control volume. As a control volume. So we can see that the important effect of the boundary layer is that there is a volume flow rate here, whereas here the volume flow rate or mass flow rate. There is a mass flow rate entering the side AC, whereas the mass flow rate leaving the side BD because of the boundary layer, the mass flow rate is reduced. So where that mass flow is going, the mass flow is flowing across CD. So, that reduction in mass flow rate can be computed by this area, because the velocity is varying. You can compute this area to calculate the reduction in mass flow rate. So the effect of the boundary layer or the wall on the fluid flow is that there is a reduction in flow rate along the direction of flow, and correspondingly there is a displacement of fluid particles in the transverse direction. This is the flow direction. The transverse direction to fluid motion, there is a movement of particles. So there is a flow through the edge CD or through the side CD. And that is what is the one corresponding to the laws over here. So in boundary layer theory, the other important parameter is related to this loss of mass flow rate through the boundary layer. That is called displacement thickness. Displacement. So what is the loss of mass flow rate? That is this area we calculated. So for that, the area varies with the area varies. The area changes with y. So what we do is, for calculating the area, what we do is we take a small strip. We take a small strip at certain y. At certain y, we take a small strip like this, small strip of height. At certain y, we consider a small strip of height dy, and the reduction in mass flow rate is corresponding to small strip area, which is equal to this total velocity is u. The total velocity is the u, that is the uniform velocity, and now the velocity is only small u, and this is the reduction in velocity, and the volume flow rate through the small strip, or that is the reduction of volume corresponding to small strip height is u minus u into dv, and the mass flow rate is multiplied by rho, and this you integrate from y is equal to 0 to y is equal to this height. What is this height? Mm, this height is denoted as, this height is the delta of this particular x. So that is, you can integrate up to this y is equal to delta, or even if you integrate still beyond to any value of y, also there is no addition of area. So this integration can be from y is equal to 0 to delta or to any height infinity. So this is the reduction in, this much is the reduction in mass flow rate because of the formation of boundary. Reduction in mass flow rate along the direction of flow. Along the direction of flow. Here it is x, along x direction. There is a flow in the y direction. So there is a reduction of mass flow rate in the x direction. So the displacement thickness is defined as the imaginary distance the wall is shifted. So this loss or reduction in mass flow rate can be considered as equivalent to shifting of the bottom wall by a distance delta 1 without altering the velocity distribution. So if you assume that the velocity remains as u itself, and the effect of the loss of flow is considered as equivalent. If you consider as equivalent to shifting of the bottom wall through a distance delta 1, then what is the volume flow rate through this this area, this acted area is the u is the velocity into delta 1 into rho. So okay, this is equate this the loss of flow due to shifting of the bottom wall is equated to the reduction of reduction in mass flow along its direction due to the formation of boundary layer. So rho u delta 1 is equal to integral 0 to delta rho into capital U minus, and this rho cancels and this u get take out to take to this side. So we get delta 1 displacement thickness delta 1. Delta 1 is equal to integral 0 to delta 1 minus u by u d1. So this is what is called displacement thickness. Displacement thickness. This integral is also equal to integral 0 to infinity 1 minus u by u dy. That's not equal. So this is about loss of mass to the boundary. So because of the loss of mass flow rate, you can also calculate the loss of rate of momentum, momentum transfer, rate of momentum transfer. So again, you consider this control volume ABCD. Let us consider the same control volume ABCD. So let us consider the control volume. This is transformation. So this is U, and we have the potential velocity is uniform at the point A, whereas at the point B, it is having a distribution, and the velocity is given by u of y. Now there is a displacement, and the top of the velocity is top throughout ABCD. The velocity along x direction through CD is u, and there is a volume flow rate through the top that is given by delta mass flow rate rho delta 1 CD. This is delta 1 is displacement. So what is the momentum entering the control volume ABCD? So let us consider the control volume. control volume A, B, C, D. Rate of momentum entering is the rate of mass flow or mass flow rate, or you can say the rate of momentum rate. So I'll write this momentum rate entering momentum rate of momentum. Is mass flow rate, mass flow rate, mass flow rate multiplied by velocity. What is the mass flow rate through AC? Momentum flow rate through AC. That is what is entering. That is this one entering. So mass flow rate through AC. What is the mass flow rate through AC? Is rho. Velocity is u delta into 1. And the velocity is uniform, which is T. This is the momentum rate entering through AC. Momentum rate entering the control volume through AC. What is the momentum rate leaving? Momentum rate leaving the control volume through CD. And for that, the velocity is varying. So what we have to do is naturally we have to take at some y. You can consider a certain distance dy, and you consider a strip of height dy. And the mass flow rate is rho u dy, mass flow rate into 1. Into 1. The momentum into velocity. So one velocity is once again multiplied. And this is integrated from y is equal to 0 to delta. This is the momentum rate leaving CD. What is the momentum, not CD, BD. Momentum rate leaving not CD but BD. This is not CD, it is but BD. Now, what is the, there is a momentum leaving CD. That is CD is the top edge. CD is the top edge. Rate of momentum leaving CD. Mass flow rate is rho delta 1 U. Rho delta 1 capital U is the mass flow rate. And the velocity is same as U. Everywhere velocity is the potential velocity. So suppose the potential velocity is not changing. So this is for the case when potential velocity is not is a constant, not changing with respect to x. It is applicable for a flat plate. So u is a constant. So for the case when the potential velocity is not changing with x. So how do you consider the momentum balance or change of the rate of change of momentum? Change of momentum of flow within the control ABCD, within ABCD. What is the rate of change of momentum? So what is entering? Entering is calculated as rho capital U square delta. Rho capital U square delta. And this is leaving 0 to delta rho U square dy is leaving. And leaving through CD is also there. That is minus rho delta 1 U square. So this is delta 1. And this is rate of change of momentum in the track force. So there is a rate of change of momentum within this control volume. So because of the formation of boundary. And by momentum thickness, what does it mean is that we are treating this rate of change of momentum as equivalent to shifting of the bottom wall, that is solid wall, by a distance delta 2. To compensate for the momentum loss, the loss rate of change of momentum or loss rate of change of momentum within the control volume, that is a reduction. There's a reduction of rate, that is the change is a reduction. So the reduction is compensated by shifting the plate by the solid wall by a distance delta 2, and considering that the remaining portion has the uniform velocity u itself. And then what is the rate of momentum through this delta 2? The rate of momentum through delta 2 is, what is the rate of momentum through delta 2? Delta 2 into, in delta 2, we are considering that the velocity is u. So delta 2 into u is the volume flow rate, density is mass flow rate, u squared. So equate this with this rate of change of momentum of flow within the control, only ABC. So if you do that, okay, we will make some kind of a mathematical adjustment in writing this like this. We take rho and integral and u squared. Delta can be written as integral of 0 to delta dy, because it is y and then delta will come. So that everything can be put inside the integral, 0 to delta rho u squared dy minus rho u squared into delta 1 has an integral expression, the 0 to delta 1 minus small u by capital U dy. So that everything comes in an integral. So let me take this here. So this is like this. And the rho is constant. Rho is constant everywhere. We can cut, that is incompressible flow. Rho is constant, and u squared also can be u squared also we can take it to this side. So u squared also can be divided here. So there will be u squared will come, and then this will be u squared is divided this will go. So delta t is equal to integral 0 to delta. There's a dy is there's a 1 here, minus u squared by capital U squared is there. Then there's a minus 1 over here, which minus plus u by u, the whole dy. This one and one cancels, so 0 to delta 1 u by u, if we take outside, this is 1 minus u by capital U dy. And this is what is called momentum sickness. So delta 2 is called momentum sickness. And for y greater than delta, 1 minus u by u is equal to 0. So that way this integral can be replaced as integral from 0 to infinity, 1 minus u by capital U dy. So this is about this is about the momentum. So similarly, we can also find out what is called the energy thickness. Energy thickness. In the same manner, energy thickness is the loss of kinetic energy. Loss of kinetic energy because of the bond layer. So so I will not repeat the diagram. We can write. We can use the same diagram to write the kinetic energy at the inlet. What is the kinetic energy at the inlet? Mass flow rate. Mass flow rate, again we can write mass flow rate. We are having the rho, the velocity is the area. Area is delta. This is the mass flow rate, half mass flow rate into velocity u squared. So this is the kinetic energy at the inlet. So the kinetic energy at the inlet, that is the section AC, through AC. Then what is the kinetic energy leaving BD? Kinetic energy leaving BD. Kinetic energy leaving BD. BD is that again the strip thing we will do. So half into mass flow rate is, we must have a density. Then u is there. Then the dy is there, and we are integrating this from 0 to delta. Okay, not 0 to delta. We will not integrate first. We will find out the kinetic energy through the small strip. So half, this is the mass flow rate. into velocity half mv squared, velocity squared, so u squared, and this will be integrated from 0 to delta. This is kinetic energy dV. So then kinetic energy leaving CD, and there the mass flow rate is we know it's rho delta u, rho delta 1 u. Mass flow rate is rho delta 1 u. This is half into this into the velocity is u squared. So this is the mass flow rate. So this is multiplied by u squared. So it will become this. So the loss of kinetic energy, is half rho u cube delta minus half into integral 0 to delta rho u cube dy. So that is rho u cube dy minus half rho capital U cube into delta 1 minus half rho capital U cube into delta 1 is 1 minus. And this is equivalent. We imagine that the shifting of the bottom plate, so that by a distance theta. So the moment the energy thickness is denoted by theta, and we equate this with the shifting the loss of kinetic energy by a shifting of the bottom solid part by a distance theta. So for which you get half into rho into the u cube is the velocity and theta. So we get theta. What is so u cube is divided. So the capital U cube. So here you will get 1 by capital U cube. This will go so that this half also goes. The rho goes. Rho also goes. So theta is equal to delta minus integral 0 to delta small u by capital U the whole cube dy minus integral 0 to delta 1 minus u by u dy. And this can be rewritten as integral 0 to delta dy. That is delta. So this becomes integral 0 to delta. There's a 1 here. There's u by u whole cube minus 1 plus u by u d1, and this will go. So it is integral 0 to delta, and then 1 u by u can be taken outside, so that this becomes 1 minus u square by u square d1. So this is how energy utilized.